Hello everyone, I'm Denis Mazzucato. In this talk, I will present predictive products of abstract domains for fairness certification of neural networks, a joint work with my advisor Caterina Urban. Machine learning software is increasingly being used to automate critical decisions that can affect our lives. For example, it's being used in social welfare, criminal justice, and healthcare systems. Therefore, we expect software in this context to not be biased against subgroups of individuals. Currently, regulation authorities are moving towards this direction, such as the European Union, which proposed a first regulation framework in April 2021 that includes requirements on the non-discriminatory outcome of machine learning models. Thus, developing criteria for checking fairness in decision-making software will become mandatory soon. So, there is a need for machine learning verification tools. Here, we propose such a tool, Libra, our analyzer, to verify fairness of machine learning models based on static analysis by abstract interpretation. The class of machine learning models we are actually targeting are neural networks. Specifically, we target feed-forward neural networks with ReLU activation functions. Feed-forward derives from the fact that the network is analyzed from left to right. We provide an input vector on the left side, and for each neuron in the hidden layers of the network, we apply a computation. A computation that is the maximum between 0 and an affine transformation of the neuron values of the preceding layer. At the end of the network, we obtain the outputs. We treat neural networks as classifiers, meaning that the classification outcome of our network is the argument of the neuron achieving the higher value in the output layer. So, Libra is checking fairness of neural networks. Actually, the property we check is called Dependency Fairness, and formally, it states that the classification outcome of our model is independent on the value of the sensitive features. But let's make it clear with a simple example. We are in the setting of an interview process where the interviewer is replaced by a decision-making software. We provide our curriculum, and the software accepts or rejects our application. The goal is to check that any sensitive information will not be used to discriminate against the user. Let's assume that in our example, the gender is the sensitive feature. We say that the network is fair whenever the same curriculum, differing only on the gender parameter, is classified in the same way, both accepted or maybe both rejected. Instead, we say that our network is biased or unfair whenever the software discriminates against a curriculum that only differs by the candidate's gender. Libra is also parametric in the choice of the features that should be considered sensitive to bias. They are specified via the specification file. The first module to process the input is the front end, composed by a control flow graph generator and the one-hot handler that takes care of categorical features. Then, the analysis engine works over the control flow graph in two phases. First, the for iterator recursively partitions the initial input space using a cheap and approximate forward analysis, starting from the entry point of the control flow graph. Then, the backward analysis checks the presence of bias in each partition using the polyhedra domain and starting from the exit node of the control flow graph. Specifically, the forward iterator begins with a value representing the whole input space in a chosen abstract domain. This value is propagated through the network, producing an over-approximation of the result. Suppose this approximation is already good enough to imply a unique classification outcome. In that case, the partition is already fair, as there is no way to discriminate between the input with only one possible outcome. In our example here, this would mean that Z1 is greater than Z2. Otherwise, there are two possibilities, depending on how many ReLU functions are found to have a fixed status. By means, the ReLU x is called always positive when x is greater or equal than 0, and always negative when x is lower or equal than 0. Otherwise, it is called uncertain or not fixed. And if the number of uncertain ReLU functions exceeds a chosen upper bound u, we partition the input space along any non-sensitive dimensions and proceed again on the resulting partitions. Instead, if the number of non-fixed ReLU functions remain within the upper bound u, then the given input space, or partition, is considered feasible and passed to the backward iterator together with the relative ReLU activation pattern. These kinds of partition may represent biased regions. To ensure termination, we recursively split the input space until the partition size becomes smaller than a chosen lower bound L. Those partitions smaller than L are excluded from the analysis until a less restricting upper or lower bound will be provided. These bounds, L and U, represent the budget configuration, which controls Libra's performances, allowing trade-offs between the scalability and precision of the approach. That is why we implemented a configuration auto-tuning mechanism, which updates the lower and upper bound configurations on demand, up to the chosen threshold, minimum lower bound and maximum upper bound. The backward iterator performs the backward analysis independently for each partition. We start from different polyhedra regions, each representing a possible classification outcome. In our example, the possible classification outcomes are represented by Z1 lower than Z2 and Z2 lower than Z1. These values are then propagated backward through the network, exploiting the current activation pattern discovered during the forward pre-analysis. This to prune away infeasible executions. We split the polyhedra into two others only at each uncertain ReLU. In the end, we have a disjunction of polyhedra, representing the portion of input space that leads to specific outcome. We project away the dimension of the sensitive features and we check for intersection between regions leading to different classifications. Any non-empty intersection is a region where bias is definitely present, as all the points in the biased intersection represent data that only differ in the values of sensitive features, leading to different classification outcomes. Otherwise, If no intersection occurred, the partition is fair. Last but not least, we have the abstract domains. Libra is equipped with boxes, Symbolic, Poly, nearify abstract domains, and a generic dataset product to combine any of the above together. The abstract domains that Libra supports mostly differ by the symbolic abstraction implemented for each neuron and the ReLU abstraction function. As we can see, the best abstraction for a ReLU graph is the triangle wrapping around all the constraints, shown in blue. So Symbolic over-approximates this region with the bounding box. The Poly instead chooses a thinner relaxation, depending on which of the two has the smallest area. It chooses to relax the constraint ReLU x greater than x, or the other, ReLU x greater than 0. Nearify instead chooses a trade-off between the two relaxations, minimizing the error function. Now let's see some data. The experiment illustrated here shows the effect of the configuration budget in terms of input space analysis coverage. This experiment runs on a network composed of 5 nodes each layer and 4 hidden layers. We discovered that there is not an always best abstract domain. Symbolic, Poly, and also nearify achieve the best input space coverage in at least one test each. So we implemented a product builder, a parametric interface to construct the redacted product of any of the other domains. The reduction function consists in an exchange of bound information. In particular, this allows determining tighter bound estimation for each neuron in the network. And moreover, our approach is also generic. New abstract domains only need to implement the interface to share bounds information in order to enable their combination with other domains by the product builder. With this redacted product, we increased the precision of every other domain previously available by about 11% in the configuration with the lower bound at 0.5 and an increment of 3% in the last two configurations. In this case, we were considering the product domain of Symbolic, Poly, and nearify altogether. Again, another experiment confirms our expectations. Here, we vary the network structure from a little network with just 10 hidden errors to a bigger one with 45 each. We used small networks just to show the differences between each domain better. As we can see, Symbolic is performing well in the first 3 networks, then nearify and then Poly, but they all only achieve the second best result because the product domain always achieves the most precise result, going from a little increment where the input space coverage is already almost 100% in the smaller networks, up to even 12% in the network with 20 neurons. Libra is also able to leverage multiple CPUs. Here we show the running time required for Libra to cover the whole input space. On average, the increment from 4 to 3264 CPUs is about 5-6 times, moving from about 8 hours of running time to a little over 1.5 hours. Well, this concludes the Libra overview and my talk for today. Some words on what we are planning for the future is to extend transformers for other activation functions, other fairness notions, a smarter product domain, and to include other machine learning models like decision trees and random forest. I hope it is a little clearer on how Libra works, and we encourage you to try out our artifact. Thank you for your attention.